Let me see. Let me see.
So go through and look at it. That would be great, cool. If you have any missing though, that's not too great, right? Because I don't put the missing thing against you until at the end. Right? Because I don't want the guys working like terrible. Because I want to give you as good chance as possible. So go through, look at it. Everything missing, check it out. Don't, you're good. Alright guys, you guys are home. That's all I have for you today, man. You all have a good break, okay? Been a good year so far, man. Now we get to the fun stuff, the breaks, right? We'll see y'all later, man. Y'all be off and y'all be good, okay? Thank you, guys. Y'all be good. Later, guys. Thank you, Peter. I appreciate it.
Okay. We wait for PE. That was cool.
Hi, John.
There it is. Hey, how are you today?
I'm good. How are you?
Good.
Good, good. So I'll give a brief introduction and then right after that, we'll get started.
Great, Carl. I appreciate the invitation, and hopefully I won't bore everybody on a Friday afternoon.
No way. Thank you so much. We appreciate you being here.
Delighted.
Hey, John, how you doing?
Good, Chris. How about you?
Good. Thanks for being here.
No problem. I hope I don't put everybody to sleep on a Friday afternoon.
I'm sure you won't. You're gonna have a captive audience.
But you're making them show up?
Yeah, of course.
Of course.
But they wanted to come. And Carla, I can do the introduction if you want, just whenever you want to start.
That would be great, Chris, if you would like to do that while I monitor admitting people into the room.
Sure thing. Do we want to give another minute or so for people to file in because the number is still going up?
Yes, yes. And I'm still admitting people. Thank you.
Yeah, thanks for all you're doing getting this organized, Carla. I appreciate it.
Chris, do you want me to try?
John, are you guys operating at? Oh, sorry. Go ahead.
Should I try and share the screen?
Yeah, that's probably a good idea. Make sure that's working.
You got that?
Yes.
Perfect. Carl, it's entirely possible you might have some students from UTSI as well. I shared the link with some of them.
Oh, great.
Or they might have all decided that they were sick of me, enough in the regular situation already.
All right. It looks like we've flatlined at just over 30. Now there's another one. But we'll go ahead and get going so that we can stay on time. So today we're fortunate to have Dr. John Schmisseur joining us from the University of Tennessee Space Institute, and he is a world-renowned expert in the world of hypersonics and a great guy to get to know too. He gave me my first job out of PhD program, a fellow Longhorn, so Hookham, and he was a member of the UT band, by the way. So a lot of good history there. And so he has a hypersonics program at the University of Tennessee with a bunch of students and a ton of funding. And he was an AFOSR program manager. He's done a lot of work for all kinds of different agencies, whether it's the Air Force and Navy, DARPA, NASA, and is an AIAA fellow and just has a long list of awards and accomplishments over a really impressive career. So this John is somebody that when he talks about hypersonics, you should be listening. And so we're lucky to have him here virtually today to talk. So with that, John, I'm going to let you take it away, and I'll hang up and listen here.
Hey, Chris, thanks a lot. Delighted to have a chance to talk to y'all Roadrunners, and I guess there's some CAMEE students from other organizations that may or may not be involved. I set up my talk today with the idea that it's going to be in two parts. The first would be a broader introduction to hypersonics for those of you who are either just getting into the area or might be just interesting listeners from the other parts of the CAMEE organization. And then there's a more specific part that hopefully Chris's students will enjoy hearing about in terms of our current work, and hopefully will be translatable to those of you who are not necessarily working in the area and appreciate some of the challenges of high-speed imaging of some phenomena that take place at very high speeds. First, I'd like to ask a question first, make a request. For those of y'all who are students, would y'all mind turning your cameras on so I can see whether you're sleeping or not, and whether I need to move faster or slower, or how you're reacting, okay? Thanks, Jose. It looks like you're nodding off. I know I have to go faster.
Yeah, I'm probably a good candidate to baseline off of being the old guy in the room, probably.
No, I appreciate it. Appreciate you guys all being here, and thank you guys for working with me on this. I am going to hopefully provide some perspective to keep it interesting, but I may have over-prepared. So we've got a lot of slides for today. Hopefully there's enough cool stuff, not a lot of math, to keep it interesting. So let's go ahead and proceed. So let's see if I'm over here. Hopefully you guys can see that. First off, nothing gets done without students actually doing the heavy lifting. I think you guys can all attest to that. I want to make sure I recognize the students we had involved in this project. They're shown there with the orange outlines. We had some good computational partners on this, and got to note my good friend Chris Combs, who early on in our lab, Chris was the guy who set the tone got us on the path to success. Quite often I'm going from meeting to meeting to meeting, and Chris is out there getting it done in the lab and helping us start a great arc. And so I appreciate all he did. I think you'll find it, like Waldo, he pops up periodically in different things around my talk here. Space
Thanks, John.
Chris, I owe you thanks. But the Space Institute is an interesting place. We actually are on the reservation of the Arnold Engineering Development Complex, which you may have heard of. It's the largest collection of wind tunnels in the Western Hemisphere. And it's the development center where a lot of the work for proving out new aerospace systems from an aerodynamic propulsion point of view are done in ground testing, i.e. in wind tunnels. And so our campus is a very small campus from the University of Tennessee that's located on that reservation. It's also got the claim of probably being the prettiest college campus you're ever going to appear on. There's a vertical photograph there, and hopefully y'all can see my cursor. We only, at our peak, we had about 400 students here. Over time, things have changed, and then we're getting to the point where it's picking up again. But it's a small campus on a peninsula on a lake. It's absolutely gorgeous out in the middle of the woods. And if you like that type of thing, I can't think of a better place to work than being here at the Space Institute. We are just about an hour north of Huntsville, hour south of Nashville, between Huntsville, Chattanooga, and Nashville there. We are a campus of the University of Tennessee at Knoxville, the UT east of the Mississippi. And so I actually have a undergrad and master's from UT Austin. Now I get a paycheck from UT Knoxville. So I got all the UTs covered. There's a lot of orange in my closet. Just the tint varies depending on what kind of meeting I have or who's playing that day. I spent, as Chris noted, 23 years with the Air Force Research Laboratory, where I had a lot of chances to do a number of different things, and including working with a lot of the well-known academia our academics in the world. I learned a lot from those guys, and had a great career there. And we'll talk a little bit about some of the needs we have in hypersonics. Help me out real quick though. So about half of y'all are aerospace engineers and the rest are in environmental science. Is that right? Okay, so we're gonna try and make things as accessible as possible today, okay? And I'm gonna ask you all, it's dull, it's boring if I just keep droning on here and you guys listen and play Fortnite in the background or text or whatever it is you're gonna do. So, you know, feel free, ask a question. Let me know if I miss you asking a question, you know, feel free, I don't mind you interrupting. Let's make this a good conversation today, okay? So I'm going to begin with a little bit of motivation about why working in hypersonics is important right now and why it's become, I won't get into the details of why it's such a hot thing, but it is right now currently the #1 priority for the Department of Defense in terms of technology maturation. But I will note that throughout history, whenever the military has tried to fly faster, good things come in the future, okay? Whether that's our ability to fly around the world on transport aircraft that have swept wings and jet engines because we wanted to fly faster in the 50s, to the fact that you probably enjoy some type of cell service or Netflix on demand now because we had the ability to put things in space. A lot of good things happen from that. A lot of what we're doing in hypersonics today is going to benefit us in a decade or two when we bring down the cost of being able to go and access space. So stuff that is being driven today for building weapons is going to help us put satellites in orbit over countries that need better cell service, or allow us to put sensors over a pole or something at some point if we need to. There's a lot of benefit. I think what we're doing is going to bring down the cost of getting to space more efficiently in the next couple of decades. For those of you who aren't familiar with hypersonic, it's flying far faster than the speed of sound. And it's a term that refers both to the flight regime, the hypersonic flight regime. Then when we talk about hypersonics, we also sometimes refer to the systems that are used to fly faster than the speed of sound. And the one we all are probably most familiar with is the space shuttle, okay? And that's something that every time we send it to orbit, they would probably get close to going hypersonic, but definitely when it came back from orbit, it'd start off in high 20s in the Mach number, definitely hypersonic, and it would come in and decelerate. This is an interesting image from the underside of the space shuttle. This is an IR image taken from a chase plane flying underneath the shuttle as it re-entered, and you can see some regions of very significant heating as a result of transition in the bound air from laminar to turbulent from some unknown source on the underside of the shuttle there. And that's something that is a significant interest to those of us who work in the aerothermodynamic community. Now, Mach 5, if you read about it, is 3,800 miles per hour at sea level, okay? Now, are any of y'all from Oklahoma? No, no one, okay? If you were, I would have to translate, okay? That's about 18.5 football fields per second, okay? So at sea level, it's cooking. But the question is, every time you read about hypersonics, you say, oh, Mach 5, Mach 5, Mach 5. I actually run a Mach 4 wind tunnel, and we get all the same phenomena. Let me ask a question. Does anybody know, raise your hand and answer me, does anything happen special at Mach 5? Elijah's shaking his head. You want to unmute and tell me what's going on?
I'm not entirely sure, but like from what I've heard, like with just people talking about it, that you know, nothing special happens at Mach 5 per se. It's just kind of like the typical number that's used.
Yeah, Chris, if Elijah's your student, you got to buy him a beer or something later on. So he nailed it. Nothing special.
Yeah, for sure.
Nothing special happens at Mach 5, okay? But what happens eventually, okay? So eventually we get going fast enough, we start to get strong shocks, okay? And across those strong shocks, we get a rise in temperature. And as the temperature starts to rise, we start to have energy moving from kinetic energy into different internal modes within the gas state, okay? So that Mach 5 is like the St. Louis Arch gateway looking to the west, okay? You may be in St. Louis, but you're certainly not in Texas yet. And if you're looking out in that direction, it's the gateway to the west if you're in St. Louis back in the old days, but you weren't there yet. You just knew you were heading that way. So Mach 5 is the beginning of the broad open speed range where now we suddenly, or not suddenly, gradually, with increasing speed, are going to have to worry about where we park all this additional energy. And that energy is going to manifest itself in an increasing complexity in the gas environment, okay? At Mach 5, all my energy is basically in kinetic energy. I have to account for some thermodynamic effects, but there's no chemistry going on. There's no excited thermophysical states. The faster we go, the more I have to account for where that energy is going. And quite often it's parked somewhere internally in the molecule, and I've got to track it down and figure out where it is. And it starts to have a greater effect at that point. For very high speeds, we get to the point where the convective time is so small it can be comparable to, say, the collision time between the molecules. And at that point, things get really interesting because no longer do we have any type of equilibrium in the flow. Everything is a rate-dependent mess. And that's why flying at speeds and accounting for all that has become so difficult, because here's a simulation where there's 130 collisions that might occur around the shoulder of this nose tip for Mach 17 at 80 kilometers. At that point, you can never assume that any of your thermodynamics is equilibrium, and you have to have a rate-dependent mechanism for everything you're starting to think about. So the higher you go in the Mach number, think of it, difficulty goes as the square of the Mach number, roughly. Okay, and for those of you who are aerospace students, you also know that total temperature is going to go with the square of the Mach number, and quite a number of our other relationships as well. So one of the things that's interesting about hypersonic systems is they are probably the poster children for integrated systems, okay? If you think about conventional aerospace systems, you've got these separate functions, okay? You've got perhaps something that's going to carry your payload, the tube that you might put passengers or cargo in, and then there's wings, and perhaps underneath those wings, there's engines hung and control surfaces. When we get to a high-speed system, everything now becomes integrated, and we're going to put it all together into one multifunctional package. And that means every discipline talks to every other discipline, and you can't make a change in one without affecting something else, okay? It's highly complex. And Chris and I would always joke that, you know, the aerodynamicists are the most important part of the hypersonic work. And when you think about hypersonics, you think about the aero stuff first, but it takes a whole bunch of other things. What the aerodynamics does is it provides the boundary condition for everything else, okay? So if you're going to design a material, it's informed in the high temperatures due to the aerodynamics. If you're going to do guidance, navigation, and control, it's because the aerodynamics that you have challenges. It's the aerodynamics sets up the flow into the propulsion system. So there's a variety of things that will have to happen. And for those of us who've been working aero, we kind of touch all of them, but not because we're developing the systems, but we're creating the boundary conditions in which, or we're responsible for understanding the boundary conditions in which those things are going to occur. Now, the DoD is really emphasizing hypersonics. And in fact, you may have heard that up I-35 and then off to, is it 183 or anyhow, off to the right at Texas A&M, they've set up a new university consortium for applied hypersonics that has a good part of people interested in the hypersonics in the country working. It's the big center right now, and they just kicked it off. They're having an industry day in a couple of weeks. The DoD, in setting that up, established their list of priorities for working in this area, including materials, structures, thermal protection systems, guidance, navigation, control. You can read the list. But my point is that, you know, it's not just wind tunnel testing or CFD. There's a lot of things that are going to go into these systems. There's a lot of opportunity right now. Why haven't we done this better in the past? Okay, so we think about the space shuttle. I will argue that we've treated hypersonics like it was an exceptional technology, okay? And when I say exceptional, something that we would do every once in a while. I had a chance to tour one of the space shuttle refurbishment facilities. I think it was out in Florida at the time, but I walked in this room and was like, wow, it's dark. And then I realized that I'm standing, and this far above my head was the space shuttle. And I was standing underneath the wing, and the underside is the black tiles. The room was so dark because I was basically in the shadow of the whole thing. And once my eyes got used to it, you look around and there's this army of engineers walking around, and each one of them is grabbing a tile. We're reading the number, going back to their workstation, making sure that tile was going to be okay. It was going to take about a year for them to get the space shuttle ready to fly again after it landed the first time. Here's a trivia question for you guys, for those of you guys who are aero hardcore, okay? When is the maximum temperature experienced on the space shuttle when it re-enters and returns to Earth? At what point does the shuttle structure reach its maximum temperature? And this is not part of my talk, but a little trivia question. Chris is going to buy a beer for whoever can answer this one too, okay?
I'm going to owe a lot of beers by the time this is done.
Well, yeah. Okay, I'll give you a choice. At high in the atmosphere, lower in the atmosphere, we'll say 50,000 feet. Austin.
I'm gonna say like lower in the atmosphere.
Lower?
The atmosphere is thicker.
Well, you didn't let me finish all the options. We got higher, lower, 3 days after it's landed, or about 45 minutes after it's landed and actually come to a stop, and then the astronauts have gotten off.
I'm gonna stick with my answer, but 3 days after is an interesting response.
So actually, the maximum internal temperature of the structure of the space shuttle peaks about 45 minutes after they've landed, rolled to the stop, and the astronauts have gotten off. So imagine this thing being, incredibly loaded up with heat. It lands, and all that heat is still actually being processed and transferred in the system. So the internal substructure gets its hottest after they've landed, which is amazing. But there are a couple conference papers that actually note that. But thank you for answering. Chris will buy you.
It's like letting a brisket rest, right, John?
What's that? Yeah, exactly.
It's like letting a brisket rest.
Exactly. So one of the challenges we've had with working with things like this is we've treated them as if these things were exceptional. We'd fly them every few years. We'd get excited, and then they'd think, man, this is really hard. We're going to make this really difficult. Over time, we've gotten excited and walked away, got excited and walked away. And as a result, our workforce has essentially kind of faded out from working on these types of problems. This is from a report that the Air Force Scientific Advisory Board put together. And they noted that over time, we were losing the hypersonic workforce. And that becomes a real challenge when you have demand for it today. Today, I sat in a meeting with Lockheed Martin about 18 months ago, 2 years ago. And they said, we want to hire 500 new people to come work on our projects. And there weren't that many students out there that could go work those jobs. Okay, so there's a huge demand now. And I realized I got to move a little more quickly. So the impact on when I first started working on this up at UT, I was doing a master's program on a NASA project that supports something called the National Aerospace Plan. Okay, and there were about 10,000 people in the country working hypersonics at the time. There's about 3,000 today, and we're all a lot older. Okay, and so there's a great demand. In fact, somebody did a study and said those guys that do testing for hypersonic systems would actually rank number 10 on the world's most endangered species list. Okay, so there's a big demand right now, and we are looking for people to go and work in a broad sense across all the things in this area. What is it we do though? Okay, and I love this quote. It's getting old now, but General Schwartz, who was the chief of staff of the Air Force at the time, he was talking about tankers, and I'll let you read it. I'll paraphrase it. He basically said, you know what, we keep designing these systems and we think they're going to fly, and then they don't. Or we think they're going to function the way we design them, and they don't. They usually fly, but one of the booms doesn't work, or they don't get what he wants. But he's noted that, thinking something's going to work the first time out is getting to be pretty foolish with how complex these systems are, okay? I will argue that it's pretty straightforward to make something that you think is going to fly, but actually getting it to survive is an entire different thing entirely. And so there's a lot of folks who design high-speed systems, and they look like they're probably going to close a design, but whether or not they'll actually survive is where a lot of guys like Chris and I spend a lot of our time trying to identify those critical sources of risk. And for example, and this was the year I was born, actually a year before I was born. NASA flew the X-15A2 with a dummy pylon underneath it, a ramjet. And we discovered this incredible phenomena called shock interactions. And this was due to a shock interaction. We'll talk a little bit more about that momentarily, but suddenly you can do incredible thermal damage if you fly the X-15 in a record-setting flight at Mach 6.7 and have a shock impinging on that pylon and burn that ramjet so it falls completely off. And those of you who are aero students are probably familiar with this. Those of you who are working in environmental science, this is an extreme environment, okay? This thing started off looking like the regular surface of an airplane, and the shock wave impinging on it pretty much burned the entire thing off like you took a blowtorch to it. And today, we still spend a lot of time trying to understand the behavior of those shock, and shock boundary interactions. One of the challenges of working in this area is that we don't get to go and fly at those speeds. Okay, the entire United States experience in flying hypersonics, if we discount the space shuttle, is measured in minutes still. We have less than 10 minutes of powered hypersonic flight where we actually understand it and can capture the phenomenon. Quite often, if we're trying to demonstrate a technology, there's not enough sensors to get useful scientific data because somebody didn't want to take the risk, right? So the problem we face is that we want to predict something that's going to occur in the mission. We want to launch that system. We want to do something with it, and the access we have is at the small scale facilities that we have in our laboratory. And so one of our technical challenges is to do what I'll call intelligent extrapolation. How do I take the information I have and predict how it will scale up and apply to this mission-like scenario where right now, the way the United States is doing it, every 2 or 3 years, we'll go out and spend $500 million to get somebody to demonstrate that we can do one of these things and fly a couple of these things. And by the way, no one put enough instrumentation on it for the scientists to get anything useful out of it. We just know that it flew or it didn't fly. So challenge that way. This intelligent extrapolation piece is a big part of what we're trying to do to get better confidence in the way we design systems that are actually going to work. And if you have a chance to participate in either testing in the large scale facilities or one of these subscale flight test programs, there's a couple of them. I was really fortunate to be able to work with Australia on the high fire program back when I worked for the Air Force. Sounding rocket launch things to help us get confidence that we could scale information up to that scale and pave the way for upscaling information even more to mission conditions. Big challenge. So it's one thing to get data. To know what that data means in the context of the actual system is another big challenge for us. So what do we do? Okay, as research aerospace engineers, we study complex flow phenomena that represent risk. We go to try and figure out not necessarily how one of these systems is going to fly, how it's going to die. Okay, we look for what's going to cause something to fail, and we start to boil it down to as simple a configuration as possible. So we'll take something like a cylinder on a flat plate, and that actually represents the root of a control surface. It could represent some type of structure sticking out, and we look at the fundamental behavior of that, trying to identify how we could mitigate critical phenomena that would be relevant to a lot of other different systems. And here is one of the first images that came out of our laboratory. In fact, Chris was responsible for making sure we got this image that day. This is pretty slow by today's standards, 25,000 frames per second of a shock boundary layer interaction generated by a cylinder in a boundary layer undergoing laminar turbulent transition. And what you can see is this thing is really dancing around. And I don't know if you can see it. I've got the little bar showing it's playing here, but this interaction is really moving back and forth. And when it moves back and forth, that's incredible acoustic loads. It's like taking a small jackhammer to the surface of the airplane. This little jet right here on the backside, there's something called a triple point where the shock comes down and bifurcates. And you can see there's at that point where all three shocks come together, there's this little dark region where a jet is coming out and pinching on the surface. Is that type of jet that burned the scramjet pylon off of the X-15, okay? So that type of phenomenon, you see the way it's moving around there, incredible loads. Now at Mach 2 wasn't that extreme, right? We weren't having a lot of heating, but at Mach 7, these things turned into real damaging sources. In fact, these shock interactions are the local source of the most damaging phenomena that you're going to see experienced on a high-speed vehicle. So that's what we do, is go in and try and understand how these things tick. Just a little bit about my group. We started in 2014 and have had a lot of cool folks working for us. I finally took Chris's picture off there. It was a long time. I wanted to keep it up for a while because Chris did so much for us. But there he is in our 2017 picture. I think that's Chris's back right there, taken one day when we were all working out in the lab with the whole group of us. We want to encourage everybody to think about moving into hypersonics, and there's a space for everyone who has an interest in working in this field. And in particular, I'd like to encourage a lot of you women who feel like you got to be, those pictures of all the aerospace stuff in the back where we all look like Dilbert's boss with our white suit, white shirts, and the black ties, and we're not like that anymore. And I'd like to encourage everybody to think about how there's an opportunity for you in hypersonics if you have an interest there. Our facility is a Mach 4 Ludwig tube, and then what's very similar to what Chris is building now, and I'll talk about that. But we tried to build it at a pretty large scale so that since we're on the reservation with the ADC, and I think I've got another slide on that, but we're driven by high-speed diagnostics. So here's a megahertz pulse burst laser, up to a million pulses per second. Of course, you don't get a full second's worth; you get about 100 in train. High-speed camera. This is the type of data that we can take now at 200,000 frames per second. That's a cylinder sitting on a flat plate, similar to what I showed you earlier, but now there's a lot more detail. I love that we can see the different points where the shock is from the triple point is moving up and down, and there's actually instabilities we can see right here on the cylinder face. We'll talk more about that momentarily. So our facility kind of sits like this in this map space. We built really large facilities, okay, and ours are in orange here. Chris, I added yours to the map. But when we build something like this, the goal is to start transitioning the knowledge and the tools we have into the large tunnels that somebody's going to use to test with. We talked about intelligent extrapolation and scaling up. So we want to try and use the facilities, large facilities, to drive that knowledge and to create something. This is 60% of the scale of the von Karman Tunnel A. And when I say this, I'm referring to the cross-sectional area and Mach number of our Mach 4 facility at UTSI. So we're trying to create a gateway into more applied research due to our local stakeholders, ADC, being right there on the reservation. Okay, so what we do in our group is go back and look at those critical shock phenomena. And here's X15 again. Now this time I've circled a couple of regions that are relevant for us, okay? Where the shock interaction from the triple point impinges on the surface, you can see the damage done to the pylon there. But if you look where the pylon actually met with the body of the vehicle itself, you can see there's structural buckling. There's actually damage there. Not as easy to see in the photograph. It's circled here in the blue circles. That's what we're looking at when we look at the shock foot oscillating back and forth here in the blue circle region here. Now, we've done a lot of Schlieren, which I've been showing you, but there's another technique we're using called pressure-sensitive paint, which is really cool. And I forgot to put a slide describing how pressure-sensitive paint works, so maybe you guys let me do the interpretive dance, okay? So we take a couple of lamps here. They're LEDs at about 460 nanometers, and we light up a paint with a luminophore in it. And that luminophore will absorb photons from the paint at a particular wavelength, and then they'll emit at a different wavelength. So we illuminate with one frequency, then we put a filter on the camera and look at the intensity of the light coming off at a different frequency at a longer wavelength. Well, that process can get inhibited in the presence of oxygen. If an oxygen molecule collides with the luminophore, it'll take the photon and the photon doesn't get emitted back, okay? Well, oxygen, what do I run in my wind tunnel? Air. So now we've got a competing quenching process, and the intensity with which the light comes off the paint is actually directly proportional to the partial pressure of oxygen in the region. So now I've got paint that measures pressure. And that has been awesome to play with. So we get a time response up to about 10 kilohertz. So it's not the same as with our Schlieren, but now you can see the actual pressure field generated on this flare here and how that is creating a dynamic region here. We've got some vortices that come off that are better shown in some simulations we've got, but we use those types of diagnostics, optical type of diagnostics, to characterize the unsteady flow in our facility. Now, I want to talk about This is not what we did today. What we did today actually is that Lauren, the young lady in the picture here, passed her qualifying exam interview for moving on towards her PhD, and we're very proud of that. But when I put this slide together for another talk a few weeks ago, this was actually what we did today. And sometimes things don't go as planned, okay? And so we were running that same flare with a circle on it, and the diaphragm let go. And there it hangs on the model, and everything bends. And instead of thinking, oh, wow, we just fragged the model, all we could think of was, oh, my goodness, could you see all that cool physics? We could see shocks moving around. We could see things moving here. I'll play it one more time. This was, a bad day because the diaphragm let loose, flies downstream, takes out the model, and all we could look at was like, oh, my gosh, did you see all that cool stuff we saw? So if you
got to send me that video, John.
I will. If you react to failure like that, then you got to be an experimentalist, okay? Because stuff happens, but it's cool. But I want to point out, and I'm going to come back and hit it again, okay? We have opportunities in space for everybody who wants to pursue hypersonic aerodynamics, and you don't have to look like Chris or I to do that. And I'd like to encourage everybody who has an interest to talk to us about moving into that area. Let's see. Now, this is actually when I close my camera down. Let's see if we can do that real quick. If you ever are on Zoom with me and you see that, that's the original picture, okay? And that's actually was taken in Siberia in 2002, and I might be drinking vodka there, okay? Now, for those of you who want to move into aerospace or anything, or thought maybe I'll work for the government one day, okay? It's more than just sitting in a cubicle and trying to work out the details of things, okay? We get to travel the world, interact with other people. I never imagined I'd drink so much working for the government, doing my job, but those Russians are a special kind of people, okay? And you're in the middle of a meeting and they said, oh, today is going very well. It's coffee break. We've ordered vodka instead. You just gotta get through it. But if you want to see the world, if you want to build relationships with other people, if you want to be in a position where you're going to do something that benefits a lot of people, I imagine those of you who are I can't imagine two better fields than what are being supported in the CAMEE activity. Okay, those of you who are working environmental work get to go all over the world and interact with other countries, working on some very important technical problems. We also do that in aerospace, and I wanted to mention that for those of you who want to get outside the cubicle, what you're doing, the opportunities you have are still outstanding to allow you to go and use science to build international relationships. Okay, I was over there in Russia in 2002 because we were actually sponsoring Russian scientists, and we wanted to make sure that those guys who didn't quite have enough work to do were using their skills for useful things, and we were supporting a lot of their work at the time, and it was a very interesting experience and one I won't forget. In fact, on 9/11, I was in St. Petersburg, Russia, couldn't get home. And so that was a bit of a crazy story that probably is worth telling some other time. So I'm not done. I'm actually getting ready to do the technical part of this. But what can you guys do? So get involved with assistantships, internships. Check everything out. Don't be shy. Talk to folks here about where you can get involved. And again, I think there's a lot of great opportunities out there. I want to encourage everybody to keep looking for them. Now, what does my group actually do? We talked about shock battery interactions. The interaction between a shock wave and a battery, seen here in a couple different ways, is, again, one of those most critical sources of risk to a high-speed vehicle. And I showed you this video earlier. This is in our Mach 4 facility. We've tripped the boundary layer here, so it's turbulent, and you can see the difference in the scales of the laminar versus the turbulent boundary. There's a lot of separation in this laminar region here, okay? This phenomena also occurs inside air-breathing inlets, and we can get distortion. There's something called a shock train, which is actually a series of shock boundary interactions occurring close together that basically raises the pressure prior to combustion and the combustion process, but instabilities there can cause the shock train to be disgorged from the air-breathing inlet, and when that happens, then the Air Force considers that vehicle to be lost, okay? Now, everybody's seen Top Gun, right? Most of y'all have seen Top Gun. All the aerospace engineers have seen Top Gun. All you environmental folks, we're not so sure, right? Okay, you've had 30 years to see this movie, so I'm not going to spoil anything at this point, all right? Okay, but what happens when they fly through the other jets, jet wash, and the engine unstarts? Goose dies, right? They get into a flat spin, can't recover because their engine unstarted and they lost control of the vehicle. When that happens at high Mach number, it's worse. Okay, so we try to avoid things like that. We have to manage how shock boundary interactions behave to control these inlets. There's some really cool stuff that you can look when you just look at the pattern. So this is actually one of those internal shock interactions, okay? And this is done by a computation, my good friend John Podgy at Purdue. They were computing this, and we were saying, hey, John, all those flow features you're seeing where this ramp here is generating the shock wave, and then as it interacts with the sidewalls, there's a lot of vortices and things that roll up. We had a fin running in our tunnel and actually we're doing luminescent oil flow. And you can see in the corner is the exact same type of structure that John is seeing in their simulations we saw in our experiments. And so we've always enjoyed putting these two pictures side by side. The point being that there's a very complicated set of phenomena that occur inside these high-speed inlets, and managing them. When you see something like this in the corners, this inlet's getting ready to unstart and potentially do something because this is all distortion. Okay, the boundary layer, the viscous region growing on the side where the flow is slowing down, is actually causing distortion, and those are regions that are ripe for the shock to separate and eventually get pushed out the front of the inlet. So we're interested in transitional shock boundary interactions. And I'll tell you why momentarily, but we ought to begin by defining what the boundary layer is and the difference between a laminar and a turbulent boundary layer, okay? Now, anyone who's a golfer is probably very interested in turbulent boundary layers. That's why there's dimples on golf balls, right? So I can drive one farther, okay? And that has to do with energizing the boundary layer. But this is a picture of a Mach 5 boundary layer. Up here, this is probably a transitional boundary layer. It looks laminar, okay? Because it's nice and smooth. We can see laminar from, I think this root word, the same one as laminate, nice smooth layers that glide over the top of each other. Eventually, there are instabilities growing in this, we just don't see them. But as those instabilities drive the breakdown to turbulence, then what happens is there's an energetic mixing, okay? And high energy flow from out here at the edge of the boundary in the free stream gets pulled through the motion of eddies down closer to the surface, and the resulting velocity profiles become much fuller. This is a Mach 2 laminar profile. You can see the sonic point's about 40% off the wall. The turbulent profile, that sonic point is pulled down much, much closer, maybe an order of magnitude closer to the wall. So the turbulent interaction is far more energetic, okay? What we're interested in is understanding how these shock boundary interactions behave when a boundary layer is transitioning from the laminar state to the turbulent state. And one of the reasons we're doing that is no one's really looked at that in the past. So in the 50s or 90s, I would say 50s, but in the 90s, for the last 50 years roughly, we've always thought that aerospace vehicles were going to be huge. In fact, in the 1990s, there was a study done, and they said, well, we're just going to look at turbulent interactions because those will be the ones that are going to happen on these big vehicles, okay? And then we started making more progress in understanding how the boundary transition process occurs, and we started thinking, okay, before we fly giant air breathing systems, the first thing we're probably going to field are going to be weapons. They're going to be a little smaller. As a result, suddenly we're thinking about laminar turbulent transition taking place over maybe half of the vehicle scale. The transition process can take a long time. And so now transition is going to occur over a considerable part of the vehicle, that breakdown from laminar to turbulent flow. And we're starting to design for extended regions of that. So these things that we pushed aside as, they're not relevant when I was a student are now probably the pacing issues for new designs today. And that is, how do these interactions behave when the boundary layer is actually transitioning between the two different states? And so that's what we study. These transitional interactions can behave very differently. And for example, let's look at two videos we've seen already. Here's a laminar interaction. We can see there's a very large separation region here. This is the laminar region because it's it's not as energetic, it's susceptible to pressure gradients that will cause it to separate. And so you can see there's a very large footprint of that interaction, and it's very smooth up here, and it becomes turbulent when it attaches. That turbulent interaction, driven to turbulence because we had a sandpaper trip here, very little separation. You can hardly detect it in there. Both of these, the laminar looks pretty steady. The turbulent is known to be somewhat unsteady, but if you compare this transitional interaction, that one that's bouncing back and forth between the two states is some of the most unsteady phenomena we see on one of these systems. Are you guys with me so far? Is anyone bored? Okay. I could tell another comb story if that helps, or okay, not
I'm riveted right now, John.
What's that?
This is the part I've been waiting for.
Okay. So this is the part we're working on. We do a lot of our work just with Schlieren system, okay? And Schlieren is one of the most ancient techniques that we use in aerospace engineering to visualize the flow, okay? We basically are going to pass a collimated light beam through our test section, detect how density gradients, similar to the mirage effect, are going to bend the light, okay? Image it back onto an imaging source and then look at it in camera. And we basically can use that mirage type effect to look at to detect density gradients. So basically, the Schlieren allows us to identify density gradients in the flow field. That's something that people have taken still images of for 100 years or more, but now we've got high-speed cameras. And so now we do that at 400,000 frames per second. These are the phenomena we're interested in, okay? And so we have an envisaged shock generated by a cylinder here. That cylinder is just a canonical configuration that represents some type of feature on the vehicle. It's bifurcates into a front forward shock and a rear closure shock. In between, there's a separated region here. And these transitional interactions have their own unique shock wave that no other interactions have, called the upstream influence shock. And we'll talk a little bit about where that might be correlated with momentarily. And so we try to track these features. We've used oil flow, similar to what I showed earlier, to verify that our boundary layer was in the different, our interactions were transitional or fully turbulent down here. Or we never got a really laminar one because, we were limited in where we could take measurements. But you think about it, we've got this boundary layer undergoing, it's a very delicate thing, it's very thin, and the last thing I want to do is start drilling holes in the surface for pressure taps, because now I'm going to create perturbations when I do that. I'm going to disturb it. So we try to do all our measurements optically. And so we went in and actually tried to measure what other people conventionally would put, say, a pressure transducer here, and watch the shock oscillating back and forth over the top. We did the entire set of experiments optically, and we're, I think, among the first people to try and do that. And Chris had the lead on how we did that analysis. In fact, this is Chris's slide here. What we did, frame by frame, wrote a shock tracker algorithm to go in and locate each one of these, and would track, so over 50 or 100,000 frames, the location of different shock waves. And then you had a statistical data set, and you can start to look at the statistics of shock motion. So this is a probability distribution of function, or a histogram of the shock foot location, okay? And what we have here is we see that the typical turbulent interaction for the forward separation shock, the boundary layer comes in, conventionally for a turbulent boundary layer, it will separate at the separation shock. There's a recirculation region here. Then this back closure shock closes the interaction, reattaches, and here it's occurring right at the base of the cylinder. What we see is the transitional interaction, shown in blue, has a much larger footprint. It's actually moving around a lot more. If you're designing an aerospace vehicle and you're wanting to account for that dynamic motion on the surface, a transitional interaction has a lot more acreage you have to think about 50% more in this case. The other thing we've seen is that these things, for the transitional case, and we were the first group to really see this, and this actually caused a lot of head scratching. We see some very intense spectral peaks that are not typical of what you would see in a laminar interaction or a turbulent interaction, which is shown down here. By comparison, here's a transitional interaction in black. The turbulent is shown in blue, and you can see that the blue has kind of a broadband focusing of content there in about the 5 kilohertz region. a very pronounced resonance in the transitional interaction, the first thing we said is, well, what are we doing wrong? This is clearly wrong when your instruments do that, right? Over the next couple of slides, I'll show you where I think we're actually right. So what we see in our transitional spectra are clearly different. And I will argue that we were among the first to bring this to light in the aerospace community. And I think we're still trying to figure out what we do with this. But how do we know what we're seeing is fluid dynamics? Okay, because we thought we've had all kinds of questions. Something's vibrating. The plate's not, your shock generator is not screwed down appropriately. You've got a structure that's moving. Clearly, you did something wrong, right? Okay, and I was asked to explain what GFF is. Okay, so GFF is basically the power computed in a specific frequency F. So that's the power spectra. If you were going to calculate it, you would take the FFT and then normalize it by the variance of the signal. So this is basically a power spectra, and each value at a particular frequency is the energy of the signal in that particular range. Now we've normalized it by F here, and that is called pre-multiplying your spectra. That is something that is done to bring out some of the low frequency content, so it doesn't look like a it doesn't look like just a standard roll off. It helps us pull out and compare some spectra. And people have been comparing the spectra this way for shock interactions for quite a long time. But so the question is, how do we know what we're seeing is fluid dynamics? And I asked one of my PhD students this question, and we had to go back and actually regenerate a couple of figures. So we've plotted the peak frequency, and the student plotted the peak frequency and said, okay, here's my frequency. And I looked and said, aha, it is fluids. Okay, how do we know this? And the student said, how do we know that? Why did I feel good about this? Because our frequency is diminishing as our boundary layer is growing downstream. The boundary is going to start at a certain state, and it's going to grow downstream, or as it moves downstream. And we ought to see that for the transitional interactions, they're going to keep diminishing. That the peak frequency will drop as the boundary layer keeps getting thicker. Okay. This is a turbulent case out here, and it's different than the others. But in case you want to see it slightly differently, we convert it to screw-all number. And then if we multiply by the square root of x, because the laminar boundary layer in which these transitional instabilities are growing actually grows proportional to the square root of x. Actually, you remember delta over x is proportional to a constant over the square root of the Reynolds number x. Anyhow, not too much detail there. But now everything collapses. It's all linear. Okay, so whatever we're measuring grows exactly the way a boundary layer is going to grow. In fact, there's an inverse relationship. As the boundary layer gets thicker, the peak frequency is actually diminishing according to the growth of that boundary layer. So there's something is going on here. We went ahead and tried a different diagnostic technique. We used this pressure sensitive paint and found that, in fact, for the transitional interactions, we see that same focus peak. And for turbulent interactions, it's not there. And then a few years ago, some guys from NASA Langley actually computed our case using direct numerical simulation. That is free of turbulence models. And there's the same resonant peaks in their simulations. They were actually able to reproduce the observations we see in our experiments. Okay, so we believe it's real. Okay, but what is it? What's going on? And we're still trying to figure that out. But I can give you a couple hints of where we think we're going. So we changed models. I won't get into the details of that, but we actually showed that it wasn't the model. It was actually on a cone. You can see the exact same thing. Then Chris did some 2D spectral analysis that I thought was really interesting. And I'll go through this kind of quickly. So you take an individual point, any point in our image, you can collect a time history of intensity. And with that time history of intensity, now it's like a single point measurement. You can do spectral analysis on that and calculate a frequency peak. Let's average the energy over a certain bandwidth there, and then at a different pixel, map that energy content in terms of a heat map back onto our signal now. So now we can build a heat map of where the action is going on in all our images over time, okay? And again, Chris did all this work. But now we see that the transitional case on the left and the turbulent case on the right behave somewhat differently, okay? As it turns out that there's two hypotheses for where the unsteadiness from one of these interactions comes from. Okay, some people say that the interaction is an amplifier, that perturbations in the free stream coming in hit the interaction and then get amplified in the shock interaction. Others say that there's an instability in the shear layer here, and it will oscillate, causing the low frequency unsteadiness to actually originate from within the separated region. And what Chris's heat maps are showing us that ours do both. Okay, so it turns out the turbulent interaction here, all the motion in the range that corresponds to our unsteadiness in the 2 to 6 and 0 to 2 here occur at the shock itself, like the shock is moving back and forth. In the transitional case, all the content in the interstring frequency range is occurring here in the separated region. In fact, Chris did a cross correlation of that and found that there was a peak velocity differential of about 100 meters per second. And if you look at simulations, the only place we see 100 meters per second in our simulations is right there in separated region. So whatever's going on in the transitional case appears to be originating in the separated region. Whatever's going on in our turbulent cases appears to be driven by the shock being driven by something else. And we thought that was very interesting. We actually have a case that falls into each camp. So let's see. Now, we saw something else here that had never been seen before, we think. And if you look at this, we went in, this was 200 kilohertz Schlieren, and we're watching, and we've highlighted it with the green line here, but if you see this little region here, in a conventional shock interaction, the separation shock here is where the boundary layer separates, and this region occurs earlier. And when our PhD student came in and said, well, I've got this region of upstream separation, I said, you're wrong. There's no way that happens. That's not the way the model works. Okay? And so then I sent her back to fix it. And then she came back and said, no, I had to apologize later because that's actually what we're seeing. And so what we have here is this interesting phenomena where in the transitional interaction, there is a precursor separation region that's actually oscillating back and forth upstream of primary separation. So you've got the separation shock, you've got a large scale region of separation, and there's this small finger of separation that's actually pushing upstream in the boundary layer. We don't think of a supersonic boundary layer having disturbances propagating upstream, but recall we have a essentially laminar boundary layer in this case. Okay, on the transitional boundary layer, it behaves a lot like a laminar boundary layer. That sonic point is pretty high, and we believe that there are perturbations feeding upstream that are causing this to occur, and that's not typically what you see in an interaction of this type. I think we're the first people to observe this. And so turns out we see it in the cone, we see it on the Mach 2 plate. When we went back, we started looking at CFD. And one of our colleagues, Jim Coder, started looking at this. And here's the fully turbulent case where the boundary layer comes in and separates right where that shock is. And there's this interesting region here, okay? And if we actually take a closer look, that thickening of the boundary layer in the RANs is actually occurring upstream of where the shock occurs. Something appears to be moving forward in the subsonic region of the boundary layer, which is not what you intuit this thing to be doing. And it's causing this boundary layer separation precursor region. And we've got this being written up and going in one of the journals right now, and we're kind of interested in where this is going to develop. Now, our goal is to push on to higher speed flows as well. Okay, and so this is a hollow cylinder flare. Here's more of our Schlieren, some complementary CFD, and you can see these streaks occurring on the surface. What we're interested in now is understanding how these types of interactions behave in the presence of a varying boundary layer laminar turbulent transitional. And here's some of that pressure sensitive paint data I was telling you about earlier. We're really excited about this. When you see the CFD images here, and perhaps here they're better apparent in the skin friction plots where you can see these vortices, these fingers rolling up the side of the flare. They're also present here in the pressure region, but when they first showed it to us, they said, can you guys help us identify what's going on in here? We actually went in and were able to measure that same phenomena. You can see the vortices starting there in the paint. We're excited about what we're picking up there with the paint, and it's not often that that CFD will find phenomena, the experimentalist guys go and verify it. It usually goes the other way, but we're excited about this, and I think right now we've got another campaign going on the tunnel with a slightly larger model. We're doing more paint work, and that's going to be coming out this week, and hopefully we'll be publishing it next summer. Now, to fully understand what's going on, we need to be able to characterize this incoming boundary layer. That's one of the most difficult things we can do. These things are very thin, okay? And getting that state of laminar or turbulent and what the content is a research question that a lot of folks in aerodynamics are trying to ask right now. So again, using optical methods, going back to Schlieren, we've been able to build a transition tracker based just on our Schlieren signals. And so we can go in. Key here is if I had a flat plate model that we were looking across the entire boundary layer, we wouldn't be able to see all the way across it with the Schlieren. We'd be integrating across the entire flat plate. So you use an axisymmetric model, use a cone, use a hollow cylinder flare. When that boundary layer develops here, then your Schlieren or whatever optical diagnostic technique images across tangential to the edge there, and you can actually resolve structures. So here's a raw image here where we can see the boundary layer is developing and then it's starting to become unstable, and now we've got turbulent characteristics down here. And so just from an imaging point of view, we can go in frame by frame, and if you calculate the RMS of your local collection of pixels and find when the pixel average RMS over a particular region exceeds a certain threshold, you can identify the transition location. And so building that transition location, we were able to develop an intermittency distribution along the surface of the hollow cylinder here. And what's behind it is the spectral content of each individual pixel. So what we see, the intermittency distribution gives us the percentage of time that the flow is turbulent downstream of that location. So for example, down here at about 150 millimeters, the flow is always turbulent downstream of this region. Up here at 100 millimeters, the flow is always laminar upstream according to our cumulative density function here. If you look at the CDF, you can see that it in fact marks the demarcation of a rise of high frequency content in the boundary layer. This in the back is a waterfall spectra. And you can see that it lines up exactly with the rise of our higher frequency content then. So we're using these optical techniques to go ahead and identify regions of instability in the boundary layer as well, but that's probably not quite good enough. Okay, we'd like to have a little better measurement. And so now we're going to use a technique called a focused laser differential interferometer. And in this case, and here's a photograph of it here, you know, the iPhone animates things now, right? But so there it is deployed in our Mach 4 Ludwig tube. We're going to take two sets of two beams, okay? And basically it's a helium neon laser. What we'll do is we'll polarize it. So now we've got two beams that have slightly different polarization, and we'll pass them through our test section. We'll bring them to a focus in a certain region here. Then we'll recombine them on a photodiode. Any type of turbulent structure that passes between the two beams that compose each individual probe location will show up as a time-varying signal here on the photodiode. Okay, so we're basically taking an interferometric technique, focusing it down on a diode and using it to make a localized unsteady measurement. And now we can measure fluctuations in the flow field at well over a megahertz. The instrument's sensitive into the tens of megahertz. If we have a turbulent structure moving through the flow field, then if we look at the cross correlations between two different FLDI pairs, now we can measure a convective speed. And you can use these to detect the local frequency content within the flow or the convection velocity of turbulent structures if you use a two-pair layout. And here's a velocity profile of a turbulent boundary layer on the floor of our Mach 4 tunnel. So generally the idea, we're basically going to interfere two laser beams and make a measurement that way, okay? Now to do that, we had a student go in, and there's our high-speed Schlieren again.
And by the way, John, I'm just going to interrupt to say I hope my students were paying attention to that slide because we're going to want to be able to do that at some point.
Oh no, you're going to do the next slide, Chris. We're going to show you something that you're going to completely bypass that, okay?
All right, sounds good.
I'm going to show you something next I think is really cool. And guys, by the way, we're almost done. I got like 3 slides left. I'm sorry I'm running a little late, but we're almost done. So here's 3 different locations and the spectra we might measure. So out in the free stream, we just kind of get this signal that looks like tunnel noise. And it turns out in the laminar boundary layer, the spectra is not that really, you can't tell much of a difference between the free stream and the laminar boundary layer. There's not a lot of turbulent content in the laminar boundary layer. It just looks regular, okay? But here, as we start to get into the interaction, what do we see? We start to see general noise levels are rising. And here at reattachment, we've got a lot of spectral content. And if we look at a characteristic scale of the boundary, we just say, okay, the boundary layer is about 3 millimeters thick at this point. We've got an edge velocity. We can calculate some representative of frequency represented by the orange line here. You can see that the turbulent structures associated with this will be higher in frequency. This will be kind of a minimum for that region. And out here, that region is really starting to flare up as we start to measure the turbulence. So I'm not showing the results today, but we've got a student who's now measured the evolution of the boundary layer on our hollow cylinder using this technique. This is a kind of a standard technique now in high-speed aerodynamic measurements, but we're rolling it out and using it to characterize what's going on with the upstream boundary layer here. But even this, you get 1 point for every tunnel run, and Chris's students don't want to do that. Okay, that is a miserable experience to go out and set up a tunnel run just to do one thing. So why don't we do it this way? Okay, so this is a diffraction optic that we put in the beam path. And Chris, you guys can now do a 6x6 grid of points here. Here's the one
oh yeah, this is the thing you were telling me about. You're right.
Yeah.
We're gonna skip the other thing and do this instead.
Okay, so this week, Mark Gregston, who came in and followed on in Chris's position in my group, is at Texas A&M running their Mach 6 quiet tunnel. And Mark is running a 6x2 array of FLDI pairs. And so every time they run the tunnel, he takes a boundary layer profile shot of what's going on. And because it's a transitional boundary layer, he's getting a lot of just spectral content there. We've measured the second mode instability. Stuff looks really cool there. But now if you put these diffractive images in there, now we can start to measure grids, okay? And imagine going into a turbulent boundary layer with your grid and actually being able to measure vorticity or a range of Reynolds stress fluctuations, all kinds of things with that, because now we can make more than 1 point and get time resolved measurements at multiple points. And here's just a proof of concept with that on an underexpanded jet, where we made 6 simultaneous measurements, and all 6 measure the 17 kilohertz tone in this. That actually agrees very well with some microphone measurements and Schlieren measurements we've made as well. So Chris, I think you guys want to do the FLDI, but you want to drop this diffractive optic in there and do the multi-point thing, because that's looking like it's going to prove out really nicely.
Yeah, exactly.
I'll share with you guys.
That looks really nice.
So we're doing a lot of stuff trying to measure time resolved phenomena. And again, a lot of times for the boundary layers we want to measure, you can't go in and put a probe in because you're physically disturbing the flow at that point. So optical techniques are a desired way to do this. We're working out a lot of details along the way, but we're excited about where we're going. And I think this linear FLDI system is going to be really cool. Now, one of the things, since everybody likes outtakes, right? I thought I'd show a couple other things here just for fun to end, and then we'll get to questions, okay? So here's another lost diaphragm. This is what happens when you just get a particle that moves downstream. And this one, we spent a lot of time looking at. We think what's going on is there's a very small particle that's hit the front of the cylinder and is now bouncing back upstream, stalled out, and now wrapping back around the cylinder. But that's why people are interested in weather effects for hypersonics. Imagine you fly your hypersonic system through a rainstorm, and now your shock deforms in such a way like this, okay? So this is just a small particle bouncing off the face of the cylinder at 200,000 frames per second. You know, I can't, you blink your eye, it's over. But this is what it looks like. And if you look at all the cool phenomena going on, we're actually trying to replicate that now. Again, diaphragm loss, and then this was us just burning all the hair off Mark's arm playing it. The new Schlieren system was set up that day. And so when you guys think your professors come back from lunch, they're like, oh yeah, I'm going to go review a journal article, or I'm going to put my lecture together. No, heck no, we're going out to the lab and we're playing with stuff, okay? And so this was a propane jet and a can of air duster, which we later realized was also flammable. And so this is what happens if you're doing turbulence. There's a nice laminar flame in the turbulent jet, And then all kinds of new turbulence scales as gases of 2 different thermodynamic states and 2 different molecular compositions interact with each other. And that was a lot of fun, and Mark's hair grew back. So with that, I'd be happy to answer any questions, and hopefully it was mildly interesting. Oh, by the way, Chris's team, we like Mylar diaphragms because we can actually wipe the windows off after we left skid marks on the windows when the diaphragm goes screaming downstream and leaves a mark like that. Those wipe off later on. Our Mach 7 is going to have metal diaphragms too, and we are sweating a little bit about that. So be careful with your windows. Okay. All right. Does anybody have a question?
Hi, John. Maybe I'll start. The last Schlerin you have shown is very interesting because our group have been doing a CFD of a plume with different helium in air, and we got some very interesting structures like that. So it's very exciting to see that turbulent jet and a plume, especially when you have more buoyancy than momentum. The structures are even more interesting because it generates a new type of turbulence. So that's something hopefully at some point, if you're interested, we'll be happy to work with you. So
oh, absolutely. You know, I'm happy to share any of this stuff, or we can go shoot. You know, actually, Chris's guys ought to be very competent in taking this stuff too. But you know, you're welcome to copies of these things like this. I show this in my turbulence class.
And I have a few other questions, John. So regarding the transition, I think that's very interesting. The fluid mechanisms you have shown. A few questions. I was just wondering, how do you initiate the transition?
So we try to let it happen naturally. And so one of our problems is that when we trip it, all right, we can have something, but now we're not quite sure what the content is in the boundary there because we're putting a lot of content in there. So we try to let it happen naturally. And the reason we're going with the FLDI is to try and measure the growth of the instability so we know what is driving the transition process. For something like this at Mach 4 is probably a TS instability, where it's too low for second mode. So we really just have probably a TS mode that's going to be growing in there. I don't think we've got a capability to identify whether it's a oblique mode or something else, but we're going to assume that it's just having its regular TS mode. We're trying to go back and correlate the spectral content with what somebody else might do in a simulation. So the answer is, I don't know, but we're working on it. If that's
because it looks like especially the frequency and the amplitude could be very dependent on the modes of the instabilities, right? So there could be a direct relation to that end. So
absolutely, because we're at Mach 4, the second mode is really not growing strongly at that point. It's not dominant, and so we think our Mach 4 is really driven more by TS growing. But we're going to have to go back and maybe try and separate that out a little bit. And we're hoping when we get the FLDI at work in that region there, we're gonna have a lot more. I've got a student who's done a complete FLDI survey, but everything is growing broadband, and we haven't seen a real clear mode pop out. It's more of a broadband growth at this point.
And the other thing which always confuses me is I work with incompressible flows, so having that critical Reynolds number and instabilities is manageable. So can you comment if when you have these Mach numbers, so there's a Mach number effect, there's a Reynolds number, and so in terms of, especially when you're capturing the frequency and the amplitude, how would this Mach number and Reynolds number play a role?
So as we increase in Mach number, typically at low speed, for maybe I'll give a general description. For hypersonic conditions, we really worry about 4 different types of instabilities, and the 2 that are dominant are the second mode instability, which acts like a trapped acoustic mode inside the boundary layer. And typically it's going to scale at about twice the boundary layer thickness and the edge velocity. So you can calculate an expected second mode frequency. And a lot of people go in and they look for that instability. And if you've got an axisymmetric model above Mach 4.5, that's the instability everyone is looking for. If you have a model with any type of 3D boundary there, there's a crossflow instability. And those manifest themselves as crossflow vortices. And I'm not sure that off the top of my head, I can pick a frequency range for people to look at there, but there are some frequencies associated. They also have they have stationary and traveling crossflow waves. So a lot of what people do is they're looking for these vortices to pop out in some type of simulation or experiment, and they can identify it as a crossflow instability. I think there are some correlations for particular frequencies, but off the top of my head, I can't point you to one right now. A second mode is very straightforward. And so when we look at models, we try to build a model that's going to be susceptible to one known instability. That's what you go to look for. Now, because we're in that in-between range with our Mach 4 tunnel, second mode is not really dominant yet. We've got an axisymmetric model, so we're not cross-flow. That leaves us with Gortler on the flare, and we think some of the vortices rolling up the side of the flare are Gortler instabilities. But then upstream in the boundary layer, TS is really what we think it's going to be. And I don't have a really good feel for picking out what the dominant TS frequency is going to be. I have to go back and think about that a little bit. We've been trying to primarily just pick up spectral content in our measurements. So
Okay.
I doubt that was a great answer to your question, but it's the one I can give you today.
No, that's fine. Thank you very much, John.
Sure.
I have a question.
Sure.
So in turbulent flows, can you measure the shock thickness?
So if the shock is within the turbulence, it's more than likely bifurcated. Okay, so a shock thickness is going to be typically on the order of a couple of beam free paths, and generally within our imaging for the densities that we run, we generally have it spread over. It's on a pixel primarily. I doubt we'd have more than a couple pixels on it. So for the conditions we're running, we're typically not measuring a shock thickness. Now, when the shock bifurcates and we have both a front shock and a closure shock, we have some, a distributed region with the separation region in between. If we were going to try and measure the shock thickness, we'd probably be looking at it in a more rarefied set of flow conditions where there were where the molecular collisions were spaced out further, so that we have a chance to try and measure the thickness. For our purposes, what we can measure, it's essentially a discontinuity.
Yeah, but in turbulent flows, the turbulent thickness can make the shock thickness increase by 2 orders. So not many people measure it, so I'm just wondering.
Yeah, no, we haven't done a lot of that. So the answer would be there might be, but we don't pay a lot of attention to it.
Mm-hmm. Okay.
Honestly, John, I'm not sure even how we would measure it, because even you look at a technique like Schlerin, and the way that light is going to respond to that shock is not necessarily a reliable way to track.
Mm-hmm.
So you can't really, you couldn't use Schlerin, you couldn't use something like PIV. Getting that thickness experimentally would be really, really hard to do, and it is very small.
Yeah, at that point, we've got 2 competing phenomena that are both contributing to the measurement.
Okay. And in the beginning, you mentioned the thermal non-equilibrium.
Mm-hmm.
I'm just wondering, do you have any results or information that you can show? Because
not as part of this presentation.
Mm-hmm.
We will probably not see much non-equilibrium phenomena or Mach 7 tunnel, but we're trying to build a higher entropy tunnel, more of a shock tube that will allow us to look at that. But the results I'm showing today, I don't have any of that included.
Okay.
We try to limit what we're doing right now to looking at just the viscous phenomena. And so
Okay.
I operate at the low end of the hypersonic spectrum.
Is it because like in Mach 4, Mach 5, the TNE is just not strong enough?
Mm-hmm. I mean, at Mach 4, Mach 5, there's just not enough heating, and there's just not enough temperature associated with the flow. Remember, it's going to scale with the square of the Mach number. So the difference between a Mach 4 flow and a Mach 8 flow is considerable in terms of the energy content in the flow field.
Okay. Because by theory, vibrational energy should occur around Mach 3.
Mm-hmm.
Yeah.
There's not a lot of it, so there are non-equilibrium phenomena occurring in all these flow fields, but compared to the amount of energy parked in the non-equilibrium state, there's just not a whole lot of it yet.
Mm-hmm. Yeah. Okay. Gotcha.
And so from that point of view, our theory doesn't depart from a standard perfect gas theory until much higher in the Mach number range. General rule of thumb, it's around Mach 8 that we really start thinking about those phenomena and figuring that we have to account for them. If I'm doing an experiment at Mach 6 or 7, I'm really not worried about it. And particularly because to get to Mach 6 or 7, we're expanding the flow. Our free streams are actually quite cold. So
okay, it's low enthalpy.
yes, and the reason being is that, you know, and for those of you guys who are not familiar with this, when you fly in the atmosphere, there's atmospheric temperature, and it's not a huge variation compared to a lot of other things. You know, at 80,000 feet, you got about 200 Kelvin, 220, I think, is the temperature that's high in the atmosphere. That's the static temperature, and when it gets shock heated, you get a lot of energy from the traveling vehicle heating that air up, and so that air can get quite hot. We kind of do the inverse in the ground in a wind tunnel. So we're going to heat something up as much as we can, and then we expand it to hypersonic conditions. And when we expand it, it gets cold, proportional to the square of the Mach number. So a lot of the design criteria for our ground test facilities is, can we keep the air from liquefying long enough for us to get a reasonable continuum test in the test section? And if we do that, then we can test under realistic conditions, but it is super cold. And so we will eventually recover about 85% of whatever we heated the gas to ahead of time. But to get appreciable temperatures replicating flight, we quite often don't have the material upstream that can handle gas at that high a temperature. And so it's a big thermal problem on the ground. Typically, anything we test is either going to be very high Mach number with a very low enthalpy. We might get lower Mach number and higher enthalpy, but we got to do some tricks to help make that happen.
And you say that the real gas effect occur around Mach 8, Mach 7, Mach 8?
Rule of thumb,
Okay, gotcha. Thank you.
So I'm going to jump in here, and John, this has been really fantastic. So we're so glad we were able to have you for a seminar. Now, if you have another 15 minutes, I'm not sure what your schedule is like right now. Do you have a few minutes to talk to students, or do you have to run?
No, I've got plenty of time.
So what we would like to do is we'll turn off the recording, and all the faculty are going to drop off, and any students that want to hang around with you can. And then you guys can get really unfiltered, and they can ask you questions or whatever y'all want to talk about. Does that sound all right?
Yeah, they're going to realize how little I know about this stuff.
So we will. Yeah. So I'm gonna log off, and all the other faculty will get out of here, and the CAMEE host will get out, and then we'll just leave it to y'all, and you can talk about whatever you want, or you can just talk about the Longhorns.
I hate talking about the Longhorns this year, but we can talk about whatever y'all want for sure.
Yeah. Okay. All right, John, it's great to see you, and thanks again for coming. And I'm going to log off of here, and then you can have fun with the students.
Great. Hey, Chris, Kieran, Carla, all y'all, thank you so much for inviting me. I enjoy doing stuff like this. I hope it was a useful everybody's time on a Friday afternoon, and appreciate what y'all are doing. Anytime we can, support you, Chris, you guys, we're going to send you all the details we have on how to do the linear array FLDI. And again, appreciate being part of the CAMEE activity here. And thank you so much for having me today.
Awesome. Yeah. Thank you so much, John. All right. We'll keep in touch. I'll see you. You have a good weekend.
Okay. Y'all too. Chris, best of the family.